or malevolent exposure. And in that case, you want a rapid dose assessment. You're only interested in the magnitude. You don't need a very accurate dose because you want to take quick action depending on what the magnitude might be. There's individual or public information, such as studies that show what the average range of doses is for a population of a country or a particular region. And in that case, you're looking at a range of doses, again, not a specific accurate dose assessment, because it's going to be different for different people. And finally, in a compensation program, where your endpoint of interest is the accuracy of the compensation decision. So you don't necessarily need an accurate dose assessment as long as your compensation decision is accurate. So the general purpose of compensation programs is to provide timely, uniform, and adequate compensation for the people that are covered by the program. It's those who are suffering from an illness that has been determined to have been incurred in the performance of their duty. In the US, there are 3 compensation programs related to radiation exposure. The first 2 are based on nuclear weapons testing. They've been around for a while. One covers civilians for atmospheric testing, downwinders, and the other covers military personnel who are exposed in the line of duty. The one that I'll be focusing on is a little more recent than those 2. And again, it's the Energy Employee Occupational Illness Compensation Program Act, which you might hear referred to as EOICPA on occasion. This covers workers at Department of Energy facilities and its predecessors, meaning the previous names that DOE went under. There was AEC, the Atomic Energy Commission, ERDA, so assorted agencies that preceded DOE. So the act that established this program was passed in 2000, and it established a compensation program for people who perform duties related to nuclear weapons production. And again, at DOE and its predecessor agencies. It was based on a number of findings by Congress that are in the Federal Register. So Congress determined that these activities were ultra hazardous, that nuclear weapons production and testing involved unique dangers, including exposures to radioactive substances and beryllium. So there is a compensation program related to beryllium also. I won't focus on that today, but there is a separate one that addresses medical problems that are associated with beryllium. So they went also on to find that a large number of workers at these facilities were put at risk without knowing about it and without consent for it, and that previously secret records that have since been declassified documented unmonitored exposures. And another issue was that DOE regulates, it runs the facilities and it also regulates them. And so that was part of the concern for this passage. They said, you know, it's self-regulating with respect to nuclear safety and occupational safety and health. No other hazardous federal activity has been permitted to be carried out under self-regulation. So there were 3 rules that were enacted that give the guidelines for you know, how we do things under this program. So the very basics of the act is that the individual has to have a radiation-related cancer. The program is administered by the Department of Labor. They have experience dealing with worker compensation programs, and so they were determined to be the best ones to administer the program. The analytical support falls under the CDC, NIOSH, Division of Compensation Analysis and Support. And that's who we are contracted to do work for them. The program is open to all employees who worked at DOE sites or specific time periods at atomic weapons employers, which I'll talk a little bit about more in a minute, and who have a radiation-related cancer. The claimant can be an employee or a survivor. If the employee themselves is deceased, I believe it's parents, grandparents, children, and grandchildren that can make an application for this. And the claimant must establish their employment in their cancer, so they have to provide a number of records when applying for this. The covered facilities include DOE-owned facilities, such as national laboratories, enrichment plants, and then there's a number of other sites that did assorted work in the development of weapons, and they're all covered. The atomic weapons employers are private companies that performed work related to weapons. So this was interesting. I was not aware of this when we started this, that this goes back mainly to the early days. And I should have mentioned, this goes back to about 1943. The first sites were built in the mid-40s, and so this program extends back to then. The atomic weapons employers were, in some cases, steel mills, where on their downtime, say weekends, they would use their equipment for rolling uranium instead of steel, which they did during the week. So there are quite a few of these little sites around, and there are actually around 300 covered facilities in this program. The atomic weapons employers, initially it was just during the periods where they had a contract with the DOE to do specific rolling or whatever project they were working on. It was later updated to include what's called residual periods, which includes contamination on the site. So they weren't necessarily cleaned up all that well. And so people who did not work during the contract period, but who worked there later and possibly came into contact with contamination left over from the earlier work, that's also covered. These are subject to change. There's information that's found. I don't think they're changing much now because this project has been around for almost 20 years at this point. But if new information becomes available, then dates may change or new facilities might be added. So there are two possibilities for compensation. One is through a special exposure cohort where compensation is presumptively awarded based on employment at a site or a specific area of a site. And it applies to 22 specified cancers that are determined to be associated with radiation exposure. So in this case, there's no dose assessment needed. It's just based entirely on time, location, and specific cancer. The other possibility is, at least as likely as not, that's in quotes because that's how it's stated in the Act, and that is based on a dose reconstruction. So for the SECs, the initiating act actually established four from the start. It includes the 3 gaseous diffusion plants, which is Paducah, Portsmouth, and K25, or also known as the Oak Ridge Gaseous Diffusion Plant, and Amchitka Island, where there were 3 underground nuclear tests. It also established a process for approving new cohorts. So the criteria for the initial SECs at the gaseous diffusion plants, you have to have been employed for at least 250 workdays prior to February of 1992. The 250 workdays is associated with a calendar year of work there. An additional requirement was that you have to have been monitored for external exposure or should have been. Obviously, that is somewhat subjective. There's a lot of subjective items associated with this project. It's not strictly science-based, which would make it easier, but there are politics and judgment that come into a lot of what we do. And then you have to have developed an eligible one of the 22 cancers after the start of employment. For Amchitka, since this was weapons testing, it doesn't have the 250-day workday requirement. It's just employment prior to 1974 and exposed to radiation in the performance of duty related to the 3 specified tests. And again, an eligible cancer. So I mentioned additional SECs can be established, and there are quite a few that have been added since the beginning. These can be done by somebody submitting a petition. That can be EE as energy employee. That can be someone who worked at a site, a survivor, or a representative of a labor union or somebody associated with the site. And it has to be qualified. It has to have particular information associated with it that would qualify it for review, and then evidence submitted. So it would be based on inadequate monitoring, or some evidence that records were missing or falsified, destroyed, somehow information missing so that we couldn't do an adequate dose assessment. The other method is if, the dose reconstruction team decides that we can't actually do a dose assessment, that the dose reconstruction can't be performed based on some limitation, some infeasibility. And in that case, the claimant is notified that it can't be done, and there's a petition, a form that gets done for that. And so an outside entity can make a petition, or the dose reconstruction team can say, we can't do this. And so that can be the basis of an SEC also. So at least as likely as not, and that's what we'll be talking about now for the rest of the talk. So the claim is filed with the Department of Labor. Labor verifies the employment in cancer, and they classify the cancer, which will become important later on. The Department of Labor forwards the claim to NIOSH. NIOSH performs dose assessment, and it goes back to the Department of Labor. And the Department of Labor is responsible for making the determination as to whether it's compensable or not. And that's if there's a greater than or equal to 50% probability that the cancer was caused by radiation doses incurred in the performance of duty. So the compensation is $150,000. That is the total for one employee, regardless of the number of claimants. So if the employee is deceased and the children are filing a claim, then that money gets split between all of them. If it's the employee themselves, then the compensation also includes medical expenses for the specific cancer that was incurred after the claim was filed. Again, the decision is made by the Department of Labor, and it takes into consideration the dose assessment from NIOSH. So for the probability of causation, it's based on the dose to the organ of interest. So it's this is why classification of the cancer is important, because it's the dose to the site where the cancer originated. The probability is based on National Cancer Institute risk models. And it's awarded, the probability is a distribution, so compensation is awarded if the upper 99th percentile of the probability distribution exceeds 50%. So it's very conservative, very favorable to the applicant. A number of factors are included in the risk models, including the radiation type, the dose distribution. So for internal dose, we have to look at annual doses. The age at exposure and diagnosis are factored in. And other influences are included for some cancers. In particular, smoking is a factor in the probability for lung cancers, and ethnicity is factored into skin cancers. These calculations are done with a program called IREP, which stands for the Interactive Radioepidemiological Program. This is publicly available on the NIOSH website, so anybody can go in and play with it. So there are a number of requirements that are specified in the rule for how we do our dose assessments. One of those requirements is that we use current ICRP models, and claimant favorability is required. So when there's unknown information, then the benefit of the doubt always goes to the claimant. The intent of that is to ensure that no one who deserves compensation is denied. So basically, they're looking for a false negative rate of 0, which means that we're going to have, we try to minimize the false positive rate, but there are definitely false positives when trying to get a false negative rate of 0. So the dosimetry of this program, I mentioned the 4 types of dose reconstruction earlier. We pretty much cover all 4 of these types. Occupational dose, accidents and incidents are included, medical exposure related to work is included, and environmental dose. So these are the specific forms. So we include external dose, which includes missed and unmonitored. So missed dose is dose that you're monitored for, but because of the detection limits of the monitoring method, you could have been exposed to that, but it's not detected because it's below the detection limits of the particular monitoring type. Unmonitored is just that. There's periods of time where no monitoring was performed, but we still have to figure out what the dose might have been during those times. Similarly, for internal dose, doses from intakes of material, including missed and unmonitored. And in the early days, the 40s and 50s, the detection limits associated with things like plutonium were pretty large. So missed dose can be a significant fraction of the dose that gets assigned to a person. We're also required to include dose from work-required medical screening x-rays, and ambient dose, so workplace environmental dose is included. So as you might imagine, we need a lot of data. As I mentioned, there's about 300 covered facilities. We have a group devoted to data collection. For an individual claim, a request goes to the site. If it's a DOE site, obviously we can't do this with AWEs that did a short amount of work and in many cases didn't do any monitoring, at least not internal monitoring. But for the larger sites, a claim-specific request goes to the site and they gather up all the information for the person, all the records, all their exposures, and send those to us. We've done many site visits and make data requests for more general information about the sites. We get a lot of information from the federal record centers. Some sites have closed and that's where their information went to, and that's where a number of records are archived. And also internet searches. There's a lot of information on the internet about some of these sites. So each site has its own unique concerns. So we have developed technical basis documents that detail conditions and assumptions for the major sites. Chapters include the individual areas that we're required to reconstruct. So medical dosimetry, environmental dose, internal and external dose. And there's also an overall site description that can help in the reconstruction. For internal dose reconstruction, generally these are the things you need to know: when the intake occurred, what nuclides, the form of the material, monitoring data or source term knowledge. And this is challenging under the best circumstances. If you're in an operational setting, it's sometimes difficult to get all of the information you need, and it's magnified in this, this project. So the goals are different in a compensation program than an occupational setting. The goals of an occupational radiation protection program is first and foremost, the safety and protection of the workers and demonstration of compliance with the regulations. Well, that's already all done with by the time it gets to the compensation program. So what we need to do is provide defensible dose calculations that are of sufficient accuracy to determine the compensability. So we're looking for a yes or no answer, not the most accurate dose assessment. I'll mention here, I believe that there are compensation programs in other countries that work on a percentage. So it's not an all or nothing. I believe it's based on the probability. I don't know the details, but in this case, it is all or nothing. And the percentage would be more difficult because then you would need a much more accurate assessment if you were going to base it on some percentage of probability. Can hear a couple of people talking. So this is not traditional occupational internal dose. The objective is to estimate the dose that contributes to the risk of the cancer from intakes of radionuclides. So it's not, we're not looking at whether a regulation was met, but we're looking to estimate the dose contributing to the risk of the cancer. We're required to use current ICRP models. When we started this, DOE was not using current ICRP models. They were still using ICRP 30. So we are not able to use, well, for a number of reasons, we're not able to use the doses that were calculated by the site. But one of them was because, going back historically, current ICRP models weren't used. And now that the ICRP has released, I think, all of the newer models, we will probably be transitioning to those before DOE does. I don't know when that might be, but I'm guessing we'll start talking about it soon. So the annual organ dose through the date of diagnosis is the dose of concern, not the committed effective dose. So that's very different from occupational. The most exposed organ is not necessarily important. It's the organ where the cancer originated. The tissue of interest may not be specifically modeled. There are a number of locations in the body where you can get cancer where you don't have a specific model. The organ is not modeled in the ICRP models. Probably the primary one of interest is prostate because a lot of people get prostate cancer. So that's a very common one that we see, and that's not a modeled organ. Missed dose must be included, which you would never do in an occupational dose setting. And we do include uncertainty. So, and there's a number of different distributions that can be put into IREP. So some of the challenges that we have is we can't ask for follow-up samples. Useful data about the areas, the materials, or bioassay may be difficult to retrieve, especially when we're looking at the older historical records. Samples might have been analyzed with old technology. For example, in the early days, there are a lot of gross alpha and gross beta measurements. You can't, calculate a dose from an alpha measurement. You need to have you need to know what the nuclide is. There are also a number of mass measurements that were done for uranium where we don't know what the enrichment is, so some kind of assumption needs to be made. So we also have limited information on work location and potential for intakes, which factors into having to assess unmonitored dose. We have to come up with some guess as to what the potential for intake was. The probability software, IREP, handles uncertainty in the radiation type. So it doesn't require nuclides to be entered, it requires us to enter radiation types. So we have to take each of the nuclides that we assess and convert it to some kind of, to alpha, beta, gamma, and enter it that way. So the assignment of organ doses rather than effective dose means that the nuclides that may be bounding that were used by the facility to do their monitoring might not be what would be of interest to us. So we have to go and see what other nuclides might have been there to do the dose assessment. So IMBA is our primary tool for dose reconstruction. We've put it through the paces over the last 18 years. We've used many versions of it. We have some special features in the version. Well, initially, some of these were developed specifically for us, although I think it's made its way into other versions of it. So annual organ doses, because that's what we have to assign. We had an option to be able to split the doses into the radiation components for some nuclides. It wasn't for all of them, but for the primary ones, that feature was available. I don't think that that's in the most recent version that we got, but years ago, to simplify it, because it took a long time to run IMBA when it was splitting the doses, I'll talk about efficiency measures more later on, but we've assigned a single radiation type to each nuclide for convenience. It was always claimant favorable, but it greatly simplifies things to assign a nuclide to one particular radiation type. It also includes americium growth and plutonium mixtures, which we have to use quite frequently. So the radiation type I just mentioned. So equivalent dose that gets entered is converted to absorbed dose, and then it's modified with an appropriate radiation effective, I can't remember what that stands for, but it's a distribution is assigned. So rather than a point value for the radiation type, there's a distribution associated with each one. And the categories that we have are alpha, electrons that are less than 15 keV or greater than 15 keV, and then 3 ranges for photons. The greater than 250 keV photons and the greater than 15 keV electrons are actually the same as far as the weighting. They both have a point value of unity, and then the rest of them are compared to that, or they're expressed as distributions related to that. So when looking at organ doses, this turned out to be somewhat of an issue early on, where if you're used to doing occupational internal dose, what you think intuitively is going to happen is not necessarily the case. There's not a standard relationship to effective dose from an organ dose, not one single factor. Claimant favorability, which is what we're required to do, varies by absorption type of the nuclide, the basis for the dose determination, that is whether you are monitoring the intake based on air monitoring, so a direct intake value, or if you're starting with bioassay, and the time distribution. So that's looking at the annual organ doses. And we're not looking at 50 years, we're looking at just the time from start of exposure to the date of diagnosis. So it can make a difference if that's 3 years or 30 years, depending on the nuclide's half-life, as to what's going to come out to be claimant favorable. So I mentioned that Department of Labor classifies the cancers. They use the International Classification of Diseases. There's a number of versions of that. We switched to ICD-10 last year. So the dose of interest is that to the organ of cancer origination. Because there are so many ICD codes and a lot of them don't refer to a specific organ, we developed a document that contained a list of all possible cancers, excuse me, and made a list of the organs that would be appropriate for assigning dose. So for internal and external doses, as well as medical doses. and then listed the IREP cancer model. So IREP has specific models in it for assorted cancers. So the correct one of those needs to be chosen also. I mentioned earlier that there are a number of organs that aren't specifically modeled by the ICRP, so it requires us to assign a surrogate organ. I think that's mentioned here. So for claims where the organ of origination is not included in IMBA, we use what we refer to as the highest non-metabolic organ. That's very poor terminology, and I think somebody mentioned it early on, and for some reason it stuck. But what we mean by that is that, for example, prostate, again, I would take that because as an example, because it's a very common cancer type. The dose to be assigned to the prostate would be the largest dose among the reported organs in IMBA that aren't part of the biokinetic model. So what we mean by that is the nuclide of interest is not deposited in any of the, we look at the organs in which the material is not deposited. Because the specified organs, would get large doses or larger doses because they're being irradiated from within. So we look at the ones that aren't being irradiated directly and select the largest one to assign, again, from claimant favorability. So missed dose, I mentioned, has to be assigned. It's similar to what you would calculate as a minimum detectable dose for your routine program. It's based on bioassay detection limits and monitoring frequencies, but of the particular individual. So it's not a generic program-based value. It's taking the specific claimant's bioassay results that were less than the detection limits, and it's based on that. It's used to establish the upper limit of internal dose that could have been received when the results were below the detection limit. So the thinking is that the true dose is assumed to fall between 0 and that which would result in the prediction of the bioassay results equal to the MDA. One major reason for using the MDA for this rather than a critical level is that historically, many of the results were censored below the MDA or some reporting level even. So results are often recorded even with just a less than symbol, not even a value next to it, but in many cases it's less than some value and there's no information as to what the specific values were for that count. So to standardize the missed dose calculation across the whole project, we impute these data by using half of the censoring value, which again is either the MDA or the reporting level. And half the MDA is substituted for the result and used to calculate the missed dose. It's assigned as a triangular distribution in the IREP software. So the minimum value of the triangular distribution is 0. And the max is based on the results at the MDA, with the mode being the results based at 1/2 the MDA. Environmental doses assigned. Some workers were limited to just the inhalation of airborne nuclides from the ambient environment. They didn't necessarily have any possibility of exposure or direct exposure to other things. So that gets assigned. Those are documented based on, typically based on air monitoring outside of the facilities. And for internal dose, we assign these with a log normal distribution with a geometric standard deviation of 3 to account for uncertainty. So because we're looking at every DOE facility as well as other, the AWE facilities, we have had to deal with a number of issues that have come up over the years. I think any individual site might have had to contend with some of these. So recycled uranium was a big issue because in the earlier days of the facilities, they weren't monitoring. So the issue with recycled uranium is that in the early 50s, they started reusing uranium that had already been through reactors. And so it was processed to eliminate contaminants, but there are always some that come through. So recycled uranium also includes some small amount of plutonium, neptunium, technetium. There are a number of contaminants that could be present, and we have to account for all of those when we do the dose assessments. Mixed fission and activation products. Typically, a site would monitor for cesium-137 or strontium-90 as an indicator of mixed fission activation products. But then we have to go through and figure out what the rest of the nuclides are that would go along with that and assign those doses. Plutonium mixtures, weapons and reactor grade plutonium consists of mixtures of plutonium-238, 239, 240, 241, americium-241. All of those need to be factored in. Very insoluble plutonium-239, which is referred to as super S in some cases, is known to be present at some facilities, as well as plutonium-238, where there's ceramic plutonium, mostly in the RTGs, that behaves differently than very insoluble plutonium-239. And stable metal tritides became an issue where we would have to do special assessments where at sites where those could have been present. So a particular example is the plutonium-239 super S. We actually had data from Rocky Flats and Hanford that clearly showed that it was being strongly retained. Because of the requirement to use ICRP models, we initially couldn't come up with a model, a revised model to assess this. So we had a document where we used adjustment factors to approximate the doses. It was very claimant favorable. It was pretty broad stroke where a type S plutonium would be assessed and then adjustment factors would be applied to approximate what would happen if you had the strongly retained plutonium. However, with the publication of the updated human respiratory tract model in ICRP 130, we were able to kind of kludge together a model. So we combined that with the ICRP 67 plutonium systemic model and the ICRP 30 GI tract, and we now have a model for assessing plutonium-239. That just went into effect earlier this year, and it's a lot easier to use than having to do the adjustment factors. And I should note that I mentioned we have all these data from Rocky Flats and Hanford. The ICRP 130, I think it is, actually references our initial document where we used the adjustment factors because they used some of the data that we had. So it's kind of a circle with the data, and now we can use the models. So given all of those factors, it's very difficult to do an accurate dose assessment in a limited amount of time because there are time limits on this. We want to be able to give a decision to the claimants as quickly as possible. We don't have time to make each of these a research project. So, so stepping back, looking at what the purpose of the compensation program is to estimate radiation dose to the organ of interest with sufficient accuracy, to make a compensation decision, not to be the most accurate dose assessment. So if you can do an overestimate and the probability is still less than 50%, then there's no reason to refine it any further because any further refinement would be reducing the dose, and so the probability would go down. And similarly, if you do an underestimate and the probability is greater than 50%, then there's no need to do additional assessments or refinements because you're only going to increase the probability. So we have a number of simplifying assumptions. And again, that's because we have to address the entire employment history of the person. And for some people, that can be 40 or 50 years. And we have limited time available so that we can provide a timely result. So one simplifying assumption that we make is that we assume chronic exposures for, in particular, missed doses, because we have no idea if there was any exposure at all. And so we just assume a chronic exposure unless the bioassay indicates otherwise. And that's, if there's some much greater positive results. So we have a couple of general approaches. An underestimate can be done. That would be a partial assessment of dose. And these general approaches include all of the doses. So it's internal, external, medical, and environmental doses. So although for an underestimate, it's possible that missed dose alone from internal would result in a probability greater than 50%. For example, I mentioned earlier that in the 40s and 50s, the detection capability for measuring plutonium was not very good. You could get some very large doses just based on the missed dose. And it's possible that the missed dose alone would result in a large probability, especially if it was something like a lung cancer, or somewhere that the material would deposit. So possibly liver cancer. So it's very dependent on the individual when doing an underestimate. Sometimes it's possible that it would just go compensable on the external dose alone. There are cases where people have many skin cancers. So if somebody has 10 or 15 skin cancers, it's possible that the external dose alone would put it over the 50% probability. An overestimate can be done. And if it's, so for internal, we would assign an intake that exceeds the possible exposure. If the resulting probability is less than 45%, and you see the previous one said 52, I'll talk about the 45 to 52 in a moment. So an overestimate can't be used if the probability is greater than 45%. This is typically used, again, for those non-modeled organs because you get relatively low doses for those. And in these cases, these can be generic overestimates. They don't have to be specific to a person the way an underestimate really needs to be. The primary example of an overestimate for internal dose is, this is a technical information bulletin that we have. It can be generically assigned to an individual who has no monitoring or has all of their results, their bioassay results, that are less than the detection limit. And it's based on limiting air concentration. So the maximum permissible concentration or the derived air concentration over time. It assumes chronic exposure to the person for their entire work history, 40 hours a week, every week of the year. And if you can assign that along with the rest of their doses, external dose, medical, and the probability is less than 45%, then you don't need to deal with the individual results or potential for exposure. So this is limited to specific sites and cancer locations. So the previous slides showed less than 45% and greater than 52%. That's because a best estimate is required in between there because the probability is a distribution. It's based on a random seed, so you can run it several times and get a different probability. So it needs to be more accurate when you're very close to the 50% range. And so a best estimate is based on individual monitoring, none of these global overestimates. This is somewhat misleading. A log normal distribution is assigned for doing an assessment of positive bioassay results. So a known intake, we would assign as a log normal distribution with a geometric standard deviation of 3. And these can be very time consuming, especially if the person has a lot of data. Something that we use quite a bit of is coworker data. Now it's called co-exposure data. But this is based on the premise that the distribution of people who were monitored, their doses are representative of others who were not monitored or who might have missing data. So it's applied to workers with little or no monitoring and who appear to have had the potential for intakes.
Hello?
So this gets a little tricky the way we analyze it. It's not feasible to actually calculate doses to all of the workers, so we look at the bioassay data. So the problem here is that, we only have claimants, just somebody who has filed a claim with this program. We don't know where people worked, what they did, if they're not a claimant. We do actually have large databases from a number of sites. We've either gotten hard copy records of the history of all their bioassay, or the site had a database of their own and we now have it. So we have a great deal of information with which to do an analysis. But again, we don't have the information for doing individualized doses to the people. So we assess the site as a whole. We do a statistical analysis of the set of bioassay data. So typically this consists of taking all of the data for a year, doing a time-weighted averaging of the bioassay results, doing a statistical analysis and getting a single result for a year. And then we do an intake assessment based on that. So we're kind of boiling down all of the individual's data into one person. And then we use IMBA to determine the intake rates. Again, this is a chronic intake that's assumed. We need to cover all periods of operation for a site. If there are some particularly large incidents at a site where we have bioassay data, we might do a separate acute intake for that, but typically it's chronic intakes. And we normally fit all of the possible material types for each nuclide that's included in the coworker assessment. So we assess the 50th and 84th percentile values for the bioassay data, and we fit that in IMBA. We calculate the geometric standard deviation based on those two values, and then the dose reconstructor determines the doses from those intake rates. So we publish a document with the intake rates, and the dose reconstructor then applies that to an individual. And they're entered as a log normal distribution with the 50th percentile as the mean dose that's assigned. Or if the person appears to have had a larger potential for intake, we might assign a 95th percentile, and that would be assigned as a constant rather than as a log normal distribution. So the hierarchy of data sources, this is codified in the rule. Personal monitoring takes precedence over any other data. So that could be in vivo or in vitro analyses or personal air sampling in the form of BZAs. Indicator radionuclides are used. I talked about known mixtures. So if you have recycled uranium, you have a measurement of the uranium, and then you could have some known ratios to the uranium of the contaminants in it. Then coworker data would be next. Workplace monitoring, such as general work area samples. Source term data, so identification of radionuclides and quantities available for dispersal, or a surrogate site which is sometimes used in the case of atomic weapons employers where not much monitoring was done. So there might be a site that did very similar work that can be substituted. These last three are generally frowned upon. It's harder to get those approved to use, but they are used in some cases. So once a case is done and submitted, there are things that can change. Someone can get a new cancer, which is relatively common. We get them back to assess the new cancer. And so then the probability is based on a combination of the multiple cancers. There could be a change in employment dates or facilities. From further research, the claimant might come up with proof that they worked somewhere else or had longer time than what was originally determined. We might get new information on materials or conditions at the site of interest. So our Super S document changed. So if we change a technical document, then that might change something that had been done in the past. So new methods to develop to assess doses. Or there might be additions to the covered disease list. So since we started this, there was one cancer added to the list of cancers, and that was chronic lymphocytic leukemia. And so it's possible that could change. If the claim was compensated, then nothing is done. We don't go back and take back something if the dose for some reason was reduced. If it was not compensated, then the claim is re-examined to determine if there might be a change in compensability. And so if the decision changes, then the claimant would then receive compensation. So these are the statistics as of about a month ago. This applies just to cases with dose reconstruction. This does not include the SEC cases that are awarded presumptively. So there's been a little over 36,000 cases with dose reconstruction and all the way through final decision. And about a third of them have been compensated. And then the other 2/3 are less than 50%, so they're not compensated. You can find this information on these websites. I provided a copy of this to Rich. I don't know if he's going to send it out to everybody, but if you just go to the CDC website, you can see this information, and it's updated pretty regularly. I just have a few slides that show, why there was some concern about this, why there is a program. If you look at some of the early documents, this one is from the 1940s, and it says that people were mouth pipetting radioactive material. And down here it says, oops, that should be moved up. So this block should be up. It says, as far as radiation exposure, the men are getting about 0.5 or 0.6 Rs a day, which is quite a lot of exposure. So, oh, sorry, I should mention these blue boxes are redactions of names. We get a lot of Privacy Act information on this and need to remove names from things. So additional documents, this says operations have resulted in beta ray burns of the skin of 2 individuals over the last 6 weeks. 1 may result in serious disability. Chemical separation procedures have given rise to consistently high levels of total body irradiation. And high levels back then were larger than what we would call high levels now. So the external radiation dosage have frequently exceeded acceptable standards. And the last one, chemical procedures have routinely resulted in extensive air contamination, both inside and outside the chemistry building. So resulting in hazards to both the chemists and to guard personnel who would be outside of the building. This one I just find amusing. This is not radiation because there were other concerns at these sites. So this one is there are rattlesnakes in some of the waste yards at this facility. They talked to the San Diego Zoo, who recommended that they shoot the rattlesnakes on site. They ordered a shotgun, but then a manager's recommendation was that this should not be received because rattlesnakes aren't considered as lethal as shotguns. So this is just a listing of references that were used. You can go to the website. All of our technical basis documents are on this website. Each of the site profiles that were done, guidance documents, just in general, the way that we conduct business, everything is documented on this site. So with that, I'm done. So you want to take it back?
Well, thanks, Liz. That was interesting. I appreciate it. Next,
Rich?
Can you hear me?
Rich, you're muted if you're talking.
Oh, I'm muted. All right, let me.
Rich, you paying attention? Okay. So I guess I can take questions at this time.
Hi, Liz. This is Brett Rosenberg over at the Hanford site. Thank you very much for this talk.
You're welcome.
I am relatively new to the field of dosimetry, internal and external, so I am unfamiliar with the large doses that have typically been seen in years past. So one of my questions for you, what is the minimum dose that's loosely stated, because there's external, internal, equivalent, total effective, pick a dose. What is the minimum that has been associated with a compensation? And I want to lead this into the fact that 10 rem is the magic number. And should we be questioning current ALAR practices or limits?
I don't know I'm not sure that's really a good question to ask because it's very dependent on the individual, what their particular circumstances were, their age at exposure, and how soon afterwards, after their exposure, their diagnosis was made. I don't see the probabilities and the outcomes for the most part, but I do recall hearing that there was one that was compensated at just 6 rem. Okay, and I think that was a leukemia, and I have a coworker texting me that he saw one go comp with 2 rem for leukemia. But I don't think that's common, and I don't think that should be a basis for, right, he's pointing out that's to a specific organ. Recall that that's what we're doing is to an organ, not effective dose. So I'm not sure that changes need to be made.
So an equivalent dose of 50 rem to an organ is still an acceptable annual occupational limit?
Well, I don't know that I'm qualified to discuss what's acceptable. I don't think because again, remember, we're being extremely clear and favorable. This is, compensation is awarded at the 99th percentile probability of exceeding 50%. So,
and understandable, REM is a stochastic thing. So yeah, probability.
So okay, Tom, if you're out there listening, do you have any thoughts on this? Statistics is not my forte.
I mean, the only comment I would have is just it's kind of, I don't think you can work this thing backwards. I don't think you can say, okay, we're compensating people at 1 rem, and so therefore 1 rem is dangerous. I don't think you can do that. I think you have to go in the other direction because of the things that Liz was saying, where you're really, really conservative. I mean, it's again, the idea is not to deny compensation to somebody who deserves it, and so. Yeah, I don't think you should work it backwards.
Right.
Yeah.
Okay, thank you. I do have another question. May I?
That's okay with me.
Okay. It sounds like you all make your own basis documents for the sites.
Yes.
Is that right?
Yes.
So is there information that these sites' basis documents are lacking? And if there is information that's lacking, what would you recommend current facilities include to make things easier for you all?
Well, the most basic thing is the requirements for putting somebody on a program. You know, when, at what very specific levels you monitor people, who specifically. We have a lot of issues with subcontract workers. So if they're addressed, let's see, I'm not sure what else off the top of my head. Just all of the nuclides that could be encountered. We need a lot more, I think, information than what you might include in one of your documents, but you could take a look at some of the documents we have and see what we try to address in them. But really, a really basic thing is who is on a program and why, and also why not. You know, that's, we have the hardest time determining who should have been monitored and where they were.
Awesome. Thank you very much, Liz.
You're welcome.
Can you hear me?
Yes.
Sounds like I got a little feedback. So thank you very much, Liz. I'd like to introduce our next speaker, Derek Chokish.
Thank you, Rich. So appreciate the opportunity to speak to you guys today, and a little bit about where I work. I've been at Francis Marion University now for about 21 years, and been fortunate for the last 6 years to have a joint faculty appointment with the Center for Radiation Protection Knowledge at Oak Ridge. And Rich asked me to talk about specific absorb fractions and some of the work I've done with those for both the group at Oak Ridge and the ICRP. Talking just about specific absorb fractions I've found to be a little bit dull, so I'm going to bring them into the context of the larger purpose, which is computing dose coefficients. So let me start by making a few acknowledgments. This is the group that I have the pleasure to work with at Oak Ridge. Rich Leggett and Kaylee are the full-time folks in the CRPK. Nicole Martinez, myself, and Nolan Hertel have joint faculty appointments with the group. Scott and Ken both work in Oak Ridge in other units, but are able to give time to the center, which is very valuable. And then, of course, many of you know Keith Eckerman, who's retired. Clay Easterly is also retired, but both of those individuals still make significant contributions to the work of the group. And this is my commercial. This group is hiring right now, and I couldn't think of a better audience to advertise the fact that we're hiring. If you're interested in internal dosimetry, things like biokinetics or the energy absorption side of things, we hope this might appeal to you. So there's the ad. And then the other group I need to acknowledge is Committee 2 with the ICRP. A lot of the work that I'm describing today lines up with work that's in progress, some of which has already been completed, some is about to be completed with the ICRP. So many contributions from the folks in this photo, many contributions from people that aren't in this photo. So much of the work done by the ICRP is surveying the literature for values in science that we can use. All right, so what I thought I'd do today is give a quick overview of the methodology that's involved in computing internal dose coefficients, and then obviously the focus then being the role of the specific absorbed fraction in that calculation. I'll go through the method for obtaining these specific absorbed fractions, and then some of the quality control. And then finally, hopefully end with some fun internal dose coefficient examples, go through a few cases and look at some visualizations. All right, so internal dose coefficients, what are they? Well, fundamentally, they give the desired dose quantity, whatever that is, right? So if it's effective dose, we have an effective dose coefficient. If it's absorbed dose, it's an absorbed dose coefficient. But they give the desired dose quantity per unit intake. That's what makes it a coefficient. The coefficient piece refers to the per unit intake. So what are those possible dose coefficient quantities? Well, pretty much any one of your, pick your favorite dose quantity, right? Effective dose, equivalent dose, absorbed dose. We can do dose rates as a function of time. We can use those to do annual doses, right? Elizabeth just mentioned the need for annualized doses when doing dose reconstruction as opposed to a committed dose over a 50-year time period. We can also do radiation or RBE weighted dose rates if you're interested in something like what the EPA is interested in when they do cancer risk. So our users with the Oak Ridge group, we've done work with computing dose coefficients for the NRC, the DOE, the EPA, the ICRP, and then a handful of other miscellaneous types of applications. So this latest methodology that's being implemented in the ICRP and really two series of publications that we call the OIR and the EIR. OIR being occupational intakes of radionuclides, so that's the worker. And then what's about to come out is the environmental impact. This would be doses to members of the public, which includes children. So the big changes, the improvements that are being made in these series, first implementing the ICRP publication 103 recommendations. The big thing there includes new tissue weighting factors. We're using whole body non-hermaphrodite voxel phantoms in the SAF computations. I'll come back to that point. Big improvements to the respiratory, elementary, and systemic biokinetic models. Inclusion of whole body blood as a source region, and this has caused lots of little issues as we've gone through this for the first time, but treating blood as a explicit source region in the dosimetry. Independent biokinetics for members of a decay chain. This is one of my favorite improvements. Prior to this, when we had a decay chain and an intake of the parent of that chain, progeny were treated as having the same biokinetics as the parent. And of course, that's not accurate. So now for the first time, we have biokinetic models for progeny members which are independent of the parent. So the progeny member now behaves like the progeny should when it's born in the location that the parent takes it. Improved nuclear decay data. So Keith Eckerman was one of the chief authors on publication 107, which gave us a bunch of up-to-date nuclear decay data. And then improved energy absorption models for charged particles in the gut, in the gallbladder, and in the skeleton. Okay, so going through some of the equations here, the theoretical method, and I'll try to do this maybe a little quicker because I think I'm talking to an audience that has a pretty good understanding of this. But this is equivalent dose rate, and it's the product of two terms here. The first term being what I call a biokinetic or a source term. This is the activity in some source region S. And then the second term is what I call an energy absorption or a physics term. This is the S coefficient. In nuclear medicine, it's referred to as the S value, equivalent dose to a target per transformation in a source region. And so we can break these two terms into separate pieces and talk a little bit more about them, starting with the activity term. If we integrate that activity over a commitment period, we can get a total number of nuclear transformations that can be pretty handy for us, especially when we're doing committed doses in the adult. And then the last thing we can do with that term is we can divide it by the intake activity. And when we do that, this is the piece that makes the term useful for a dose coefficient, right? This division by the activity of intake, which when we do our calculations, we're going to treat it as a 1 becquerel intake, right? So we have a dose per unit activity intake. All right, so then the energy absorption term, this S coefficient, looks like this, where the first term is the radiation weighting factor, and this presumes we're doing it for equivalent or effective dose calculations. Note, we can change this term if if the desire is for a different dose quantity. So, if we're doing an absorbed dose, then this term goes away. If we're doing an RBE weighted dose, we can put in an RBE weighting factor at this location. I know in our prior session in this symposium, there was some discussion of tabulating S coefficients for use, and that works, of course. For our purposes at Oak Ridge, because we're computing so many different dose coefficients, there is a desire to have this flexibility in here because we need a different S coefficient for each type of dose coefficient. These two terms, of course, are the energy and yield of the radiation emission. So this is coming from publication 107. And then our third term over here is, in this summation, is the specific absorbed fraction. And we'll break that down here in a moment. One little note, if we have a beta emitter, this equation looks a little bit different because we need to integrate over that beta spectrum, integrate over the energy of that beta spectrum. And publication 107 sets us up very nicely for doing that integration in a nice, easy way. All right, so let's talk about the specific absorbed fraction. So it looks like this. It's just the quotient of these two quantities, right? So in the numerator, we have the absorbed fraction, which is the fraction of energy emitted from a source region, which is deposited in a target. And in the denominator, we have the mass of that target. And it's important that these two quantities be consistent with one another, right? We don't want to compute the absorbed fraction in one geometry and apply a target mass from something that's inconsistent with that geometry we computed the absorbed fraction in. And in general, I think that it's appropriate for me to say at this point that we're looking for consistency across this whole calculation. So we want the biokinetic term to be modeled in a consistent manner with the energy absorption term, the S coefficient, the SAF. And I think we've placed a real emphasis on that in this current work, being sure that these various quantities are brought together in a way where they're consistent with our definition of the reference individual. And I'll spend more time talking about that definition. So in terms of the specific absorbed fractions, this is where we end up in the current ICRP work. So we have 79 source regions, and these are coming from our biokinetic models, places where we might have activity originating from. We have 43 target regions, and these are from the definition of our effective dose, plus a handful of others, other target regions that we might be interested in. So for example, we have lens of the eye as a target. Lens of the eye doesn't contribute to effective dose, but it is an interesting target for other reasons. We have 6 reference ages, right? The newborn, 1-year-old, 5-year-old, 10-year-old, 15-year-old, and the adult. 2 sexes at each of those ages, and then 3 radiation types, alphas, electrons, photons. For each of those radiation types, we have multiple energy points on an energy grid, 28 of those for electrons and photons, 24 for alpha particles. You multiply all those things together and you end up with 3.3 million SAFs. And so this has been my task. I'm currently the curator for the ICRP SAF set. So keeping track of these 3.3 million data points. I should add, as curator of the SAF set, that doesn't mean I've computed all of them. In fact, I've been involved in computing very few of them. My job is to collect them all and look for some of the consistencies that I mentioned earlier. Okay, so then coming back to heading towards effective dose, again, this is equivalent dose to a target. If we do this in the adult, one of the nice things is our S coefficient is invariant with time, right? So this does not have, time does not change this for the adult. The S coefficient stays constant over adulthood, which is nice. Then our integral with respect to time stays confined to the activity term. And so the equivalent dose coefficient is pretty straightforward to calculate for the adult. But for children, we do have an S coefficient which now varies with time, right? As the reference individual grows, we get a different SAF. And so this term is now a function of time, which means our time integral now needs to be performed on the product of the activity and the S coefficient. So it changes that calculation when we compute a dose coefficient for an intake in a child. Effective dose then, of course, is just the tissue weighting factor applied to the average of the equivalent dose coefficient to the 2 genders. So we take the equivalent dose to the female plus the equivalent dose to the male, divided by 2, apply the tissue weighting factor, do that summation over all the tissues defined for effective dose, and that gives us our effective dose coefficient, tau there referring to our commitment period. All right, and then a note on biokinetics, which is not where I spend most of my time, but if we're doing this right, we need to be conscious of both the biokinetic term and the energy absorption term. So this is what when a biokinetic modeler looks at a human being, I joke that this is what they see. A bunch of rectangles, and really I should add the arrows and the rate constants associated with those arrows are probably one of the more important aspects of this. So in the top left here, we have the respiratory tract model, the latest respiratory tract model the ICRP is using. The top right, we have the allometry tract model for the ICRP. So this is from publication 100. The bottom left, we have an example of a systemic biokinetic model. These would be specific to each element or each case. And then this fundamentally sets up a set of coupled differential equations that look like this. Each box essentially giving you one of these equations. They all speak to one another, and the solution to those equations gives us the activity as a function of time that we need for our dose coefficient calculations. So one more comment on biokinetic models. If we just talk about the systemic biokinetic model for a moment, I want to specifically talk about this piece up top here, the other systemic tissue. So this is a piece that can cause confusion. Other systemic tissue fundamentally is a list of 41 eligible tissues, which splits any activity in these other systemic boxes in proportion to the constituent mass. Okay, so what that means is if we have a tissue on this list that's not explicitly modeled below, then it is being modeled up here. It is part of other. So for example, if we take this systemic biokinetic model, we can talk about the gonads for a moment, right? If the biokinetic modeler decided not to include gonads explicitly in this location, then it becomes part of other, and it is effectively being modeled. It is going to receive activity. It is, we are going to see dose to that region. So then I think that points out, a biokinetic modeling decision, or at least some on a simple level, a basis for the biokinetic modeling decision, right? When should that modeler decide to explicitly list a tissue? Well, if there's evidence that suggests that for this element, it moves through that region in a manner different from generic systemic tissue, then it might be desirable to explicitly model it. And then the last point here is, any modeling decisions need to consider the impact on all tissues, right? Because of the coupling in these systemic biokinetic models, a decision to include a new compartment does impact all the other compartments. And of course, in so much as someone's interested in bringing statistical analyses to those types of decisions, I think that's a really good thing. All right, so this is my attempt, and probably a failed attempt, frankly, to generalize or list all the various sources of data that come into a dose coefficient calculation. And I keep adding things to this slide whenever I look at it again. And I could make it even messier when you consider that many of these ICRP publications have multiple references driving them, right? So multiple sources of data coming together to compute these dose coefficients. One, or I guess really these are two publications down here that are in press right now, and they're available on the website. This is the Florida group computing specific absorbed fractions in their phantoms. This is the basis then for the ICRP SAFs that we're working on that publication. We're authoring it or writing it right now. Okay, so specific absorbed fractions then. What's the method here? So we start with the definition of our reference individual. From there, we use a series of models and phantoms to compute absorbed fractions. Note that these phantoms are not the same thing as the reference individual. From those FAFs, or excuse me, those AFs, those absorbed fractions, we may need to consider scaling to conform with the reference definition. So the idea here is to use these models, but then we need to make sure they're consistent with the definition of our reference individual. And then the last thing, we've got 3.3 million of these things, so we do need a process for ensuring quality of them. So the reference individuals, one thing I will point out here is there's no image I can show you of reference individuals. There is no picture. If I was to show you a picture, it would be a bunch of data tables, right? Because the reference individual is yes, a set of idealized males and females with certain characteristics. Largely, they are defined in publication 89. We do have to supplement 89 with some additional information. Yep, masses are probably one of the most important things that define the reference individuals, but also distribution of blood throughout the body, elemental composition of tissues, some geometrical information for some regions, but in general, there is not a whole lot of geometrical information. So the reference individual, for example, the reference individual does not have a defined shape of the liver, nor does it have a defined location of the liver in terms of its proximity to the heart. So one example of some supplemental information is publication 89 does have blood distribution for the adults, but it doesn't have blood distribution for the kids. So we had to do that and publish that in 2018. So now we move to models and phantoms, and now we do have pictures, right? So again, I'll point out, these are not the reference individuals. These are the voxel phantoms that we use for absorbed fraction computation. And these are the whole body phantoms, right? Which does get us a large part of the way there. It doesn't get us all the way there. We do need some additional models. Here are some of the additional models we need. We need models for charged particles in the elementary track, right? So a lot of those come from publication 100. We have made some improvements to what's in publication 100. So this is a view of a cross-section stylized model in the elementary tract. One example of an improvement is in the small intestine now. We're using a model that does allow for crossfire from one section of the small intestine to another. We also have models, stylized models for the respiratory tract. These were in publication 66, though some revision to the source regions in publication 130. And this is a view of what the stylized model looks in the respiratory tract. We don't have age dependency in this model, which I think is unfortunate. I think that's one of the opportunities for future improvement. The gallbladder, Keith Eckerman and John Hunt produced a model for absorbed fractions in the gallbladder. And then the Wes Bolch's group at the University of Florida has a detailed skeletal model that we use where we do have age dependency in the skeleton. So when we do these computations then for different radiations, we're doing them for monoenergetic radiations on an energy grid. When we do the dose coefficient calculation later, we then interpolate to get specific energies from that energy grid. One note that does cause some confusion, we're not doing Monte Carlo alpha, transport of alpha particles in the whole body phantoms. That just wouldn't be a good use of computational resources. We know what the absorbed fraction for alpha particles is going to be, you know, emanating from the liver, targeting the liver. It's going to be 100%. So we don't need to fire Monte Carlo for alpha particles. We can use ones and zeros for those large tissue regions. For the respiratory tract, alimentary tract, and skeleton, we do have energy dependent alpha absorbed fractions and alpha SAFs. These specific absorbed fractions do include contributions from significant secondary radiations, and I think one of the best examples, an important example of that, is our electron SAFs do include contributions from bremsstrahlung generated by those electrons. And then one note on neutrons. Neutrons are handled a little bit differently. We compute those for specific spontaneous fission emitters. They're tabulated by nuclide rather than energy. And because we do that, when those calculations are performed, they have to include the radiation weighting factor, fold that in to the nuclide specific neutron SAF. Okay, so we've got the absorbed fractions from the models. We can compute a specific absorbed fraction by dividing by the target mass, but this is where we end up with a need in several cases to do some scaling to make sure that we conform with the reference individual and the masses in the reference individual. So ideally, the models and the phantoms would perfectly conform to the definition of the reference individual. Unfortunately, that's not always the case. And one of the big sources of confusion that's led to that has been about the inclusion of blood. So our whole body phantom developers did not correctly connect tables 2.8 and tables 2.14 in publication 89. Table 2.8 gives masses of organs, tissues. 2.14 gives blood distribution. And many of these masses need to have blood, their blood folded into them. So I've gone through an example here. If you look at the adult male pancreas, table 2.8 will give you a mass that's without blood of 140 grams. We need to add to that the 0.6% of the whole body blood, which is in the pancreas. So that's about 34 grams. So when you combine the two, the pancreas mass inclusive of blood is 174 grams. And so the pancreas then is smaller in our phantom than it is in our reference adult male. So we need to scale that SAF to account for that difference. So how do we do that? So for crossfire radiations, right, where our source region and our target region are not the same, there's no change, right? We don't have to perform any scaling. And I'll show you an example of why that's the case if you're not aware. This need for scaling really applies to the self-irradiation geometries. This is where source equals target. I'll note this does include partial self-irradiations where we have overlap between the source and target region, right? They're not identical, but there's overlap between the two regions. We do apply this scaling in those cases. And the scaling we apply is the ratio of the phantom mass to the reference mass. We apply that to the SAF that we compute in the phantom, and that gives us our reference SAF. This works really well for charged particles. For photons, it's a little bit trickier and well, it's not ideal, I should say. It does work well for photons when photoelectric effect is the dominant interaction. It doesn't work as well when Compton scattering dominates. So we did consider some different approaches for photons before deciding to apply this same scaling for photons as well. And one of the chief methods that we looked at was something proposed by Snyder in 1970, where you scale the absorbed fraction in proportion to the cube root of the mass. And this rule or this scaling method that he came up with was based on Compton scattering. So, and he writes when he proposed it that clearly this rule fails badly for photons of energy below 50 keV. In these cases, the AF is greater than 0.5. I'm not going to read all of this to you. Clearly for low photon energies such that the absorbed fraction is approximately 1, the absorbed fraction cannot continue to increase with the cube root of the mass. Thus, this principle should be applied only for the energy region where Compton scattering predominates, and then only when the absorbed fraction is well below 1, say less than half. Should be understood that no claim to a high degree of accuracy is made for these methods. Indeed, quite the reverse. It is evident that only a rough approximation to the dose is given. So other individuals have looked at this since Snyder published this. There are some more complex methods that you could apply to the scaling. We ultimately chose to apply a very simple approach. We like the simplicity of the the mass scaling, the non-cube root mass scaling. And part of that decision was based on the fact that we have a variety of different geometries. We do have some regions that are very large, like liver and brain, the types of sizes of organs that Snyder was working with when he described this. But we now also have specific absorbed fractions in very small regions for photons, where it would be challenging to apply some of these factors. Okay, so then quality checks. So we've got now our 3.3 million values. How do we go about looking to make sure everything's okay? And there's 4 general things we do. We look at low energy limiting values for SAFs. We look for, because we can compute those theoretically and check to make sure that we're hitting those marks. We look for age and sex dependency. We look for certain source-target relationships that speak to one another. And then one of our favorite tools is actually go ahead and compute dose coefficients and perform test cases. And one of our favorite test cases is tritiated water ingestion. We like that. It's an unlikely hero for us, tritium. But because water is very uniform in terms of its biokinetic distribution throughout the body, and because of the very weak energy, weak emission from tritium, we should get a very nice uniform dose across all our targets for tritiated water ingestion. So it's a great test of our SAFs when we do that case. All right, so here's some SAF plots. This is the adult male looking at liver to liver. And this is a little bit unusual. You may not have seen this before, but what I've got plotted are SAFs for electrons, photons, and alphas all on the same plot. Why am I doing that? Because I'm looking at this value down here, this limiting value. This is actually an energy of 0. I've plotted it as 0.1 keV just so it'll show up on our log scale. But this is the limiting value. We like that all 3 of these are hitting that same low energy limiting value. Here's an example of age dependency. So these are electrons. We're looking at source in the whole body blood irradiating the thyroid as a function of energy in the SAF. And I've plotted all 3 ages. This is in the female, or all 3 ages, all 6 ages. This is in the female. Notice I broke the scale here so that our newborn SAF wouldn't dominate so much that these all get squished together. But we like that age dependency that we see there. Here's a photon example. We see less age dependency in photons when we have a crossfire irradiation in particular. This is kidneys irradiating the adrenals. We see this little hump here that we would expect due to the close proximity of the adrenal glands to the kidneys. And then here's an example of alpha SAFs, and this is inside our respiratory tract, right? So we're looking at sources in the bronchiole epithelium, irradiating our target region in the bronchioles. And we see a very nice age dependency here. One of the reasons for this is we don't have age dependency in the absorbed fraction model. So these absorbed fractions are actually all the same. And so we've divided by the mass of the target, and you see the age dependency. So that's what we should see. We do see it. We like that as far as a quality check. And then here's an example in the skeleton, electrons in the skeleton. And what I've plotted here is in the 15-year-old female, a common target. So all of these curves are the SAF to the red marrow target for a variety of source regions inside the skeleton. And so we can look for a lot of relationships here. I could spend 15 minutes on the slide and really derail this talk. I won't do that. I'll give you one example, right? This is red marrow irradiating itself. So we like that it shows up here. We can calculate this theoretical value and make sure it hits that value. This is source on the trabecular bone surface. We can also compute this theoretical value. And we like that it takes this shape. We like that it actually crosses over red marrow here. But one of the things we like is that they converge as we go to higher electron energies, because as we go to higher electron energies inside the trabecular skeleton, the source or where the electron originated becomes less and less important as you are crossing over multiple marrow cavities and bone segments. So we like that it shows that relationship. All right, so let's look at some dose coefficient examples, just because I think these are fun. So now we're going to use the SAFs and do some dose coefficient examples. I'm going to go through these 4 cases and show you some plots. So we'll start with strontium-90 ingestion by an adult. And so what I've plotted here is an equivalent dose rate coefficient as a function of time. Time here I did in terms of age of the adult, right? So we have an intake at 25 years of age, an acute intake, obviously, going out to age 75. And for strontium-90, right, a skeletal seeker, we're pleased to see that the dose rates are highest in the skeleton, right, the endosteum and the red marrow. Kind of interesting that brain shows up, albeit showing up about an order of magnitude or an order of magnitude and a half smaller than the skeletal. That's because of the brain's proximity to the cranium. Though for strontium, that's kind of an interesting case. That would be a very non-uniform dose to the brain that we're getting from strontium-90. And really, it's the yttrium progeny that's delivering that dose. Which you can see here. If we look on the right, what I've done is broken down the contribution to the committed effective dose by member of the strontium decay chain, of which there's 2 members. And one of my favorite things to point out is that strontium-90 is really just the carrier of yttrium-90 to a location, that being the skeleton, and the high beta energy of the yttrium-90 is the guy that really delivers our energy deposition and the dose. The plot here on the left is looking at the contribution to the committed effective dose versus time. So as we go from an acute intake at age 25, you can see for strontium-90 intake ingestion, after 5 years, we've already hit half of our committed dose over a 50-year period. So, which is something I would not have necessarily predicted until you run these numbers and start to look at the why. This is the fractional contribution to effective dose by target tissue. So applying the tissue weighting factors now and looking at which tissues end up becoming more important in terms of effective dose. And remember, the dose to the endosteum was actually larger than the dose to the red marrow, but we've got a factor of 12 to 1 in terms of the tissue weighting factor there, which makes the red marrow the more significant contributor to effective dose. All right, so moving on to iodine-131 ingestion in an adult. And yeah, this one's boring, but sometimes we like to see boring. So here's intake, ingestion of iodine-131. The time axis here is days post-intake, no longer looking at years, of course, for iodine-131. This is the equivalent dose rate coefficient to, I've got 3 targets here. The thyroid, which is really the only one that matters, the esophagus, and remainder. You can see a very short peak in the esophagus as we ingest the iodine-131. Yeah. Here's fractional contribution to effective dose. Very boring, but But yeah, we like seeing boring when we expect it, right? All right, and the other thing that boring does is it sets us up for the more interesting cases, right? So here's radium-226 ingestion. I'm going to show you something a little bit new or a little bit different. The next slide is actually going to be an animation that shows you activity by source region stepping forward with time. And you're going to see two plots. On the left is going to be radium-226. On the right is going to be the radon-222 progeny of radium-226. So it's going to start out with nothing, right? Because we haven't ingested radon-222, we've ingested radium-226. So here we go. So we've got ingestion here, so we're seeing that radium go into the stomach. Time is stepping forward up here, and you'll notice that the time increments are not uniform, so they're going to speed up. They're going very slowly right now, so we can see some of the details in this ingestion. We can see radium now moving from the stomach to the small intestine, and we're getting some absorption into the blood. And because we're getting absorption into the blood, we got some uptake into other systemic tissue. Other systemic tissue can be important in these dosimetric models. And now finally, you can see we're showing up on the bone surface. We're about 1 day after the intake right now. By the way, if you're starting to look at the radon-222 on the right, one thing I will point out is I've got different x-axes here. We're very much zoomed in when we look at the radon-222 activity. And we peak now, we're about 60 days after intake, so we're 3 months out after intake, or 60 days would be 2 months, excuse me. We're about a year after now. We can still see that activity in the bone. Okay, and now it starts over. So this is radium-226 ingestion in a 15-year-old, and again, looking at the fractional contribution to the effective dose by target tissue, I don't think you're surprised to see that the big contributors to effective dose are going to be the red marrow and the endosteum target. If you remember back to the strontium-90 case, our endosteum contribution is larger here, and that's because of the alpha emitters coming from radium-226, giving us a much larger dose to the endosteum. And then here it is broken down by chain member. And anything here that shows up significant on this chart is an alpha emitter. When we look at the radium-226 chain, we have alpha emitters. We also have beta emitters, but the beta emitters don't end up making a significant contribution to the dose. In fact, I took several beta emitters off of this chart. They were included in the calculation, but I took them off of this chart just to make it a little bit more readable. And then contribution to committed effective dose over time. Again, 75% of the committed effective dose is delivered in the first 5 years after that acute intake. This is in a 15-year-old. Be a little bit different if we did it in an adult because of the skeletal model and how it changes. Okay, and then the last case, I thought I'd, since this audience is kind of interested in plutonium, we'll look at a plutonium-239 nitrate inhalation. Inhalation cases are fun. They're more fun than ingestions. And I'm going to start with another one of those animations. This is inhalation in a worker. So we've inhaled the plutonium nitrate. We can see it showing up in the lung regions, or the respiratory regions. They are all different shades of brown, by the way. Blue is different shades of blue are regions in our alimentary tract. And of course, an inhalation means you will have an ingestion. So we can see the plutonium nitrate showing up in the stomach and the small intestine. So the other thing that's fun about watching this case is where, of course, the plutonium is going to get stuck, and we'll be able to see that. So we're a couple days now after the intake. We can see this alveolar region in the lung, we are not seeing much movement there. And we're now getting uptake into the liver. We're starting to see it on the bone surfaces. We're now 2 months out and we still have plutonium in the lung, also still hanging out there in the liver and not much decrease. We're over a year, coming up on 2 years after the intake. And 10 years, and we're still in the liver and in the bone. Yeah, so that one's fun. So you can look at this stuff, of course, on a log plot, which I do think is valuable, but I enjoy watching these things. I think I learn something every time I watch them. All right, so here's equivalent dose rate coefficients then for this plutonium-239 inhalation. Our highest equivalent dose rate is in the liver, followed by the bone surface, lungs, red marrow, and then remainder. And one of the things here is I think we're struck by how horizontal these dose rates are as a function of time. When we break down the contribution to effective dose by target tissue, I think this is what we would expect to see, the liver being a significant contributor, but we've got significant contributions from multiple target regions, target tissues here. And then finally, the the fraction of committed effective dose for this case over time. This one I think is pretty unique, right? So now, yeah, 15 years to get to roughly half the committed dose, and then 30 years to get to 75%. And I think this is about as close as one can come to a constant internal dose rate over a long period of time. So my last slide, concluding thoughts. Many of these quantities are already published and available for use now. The OIR series in particular is nearing completion. The last part of that, the first 4 parts are already published. The last part will be published soon. Quantities for members of the public are forthcoming in the EIR series. And the quantities are a result of an enormous amount of work performed by many researchers and groups, both inside and outside the ICRP. And with that, I'll stop and take your questions.
Thank you, Derek. This is Brett Rosenberg from Hanford again. Are different parts of an organ taken into account, or is there justification for lumping multiple tissue types for certain organs? I'm thinking like adrenal cortex versus medulla.
Yeah, in the radiation protection models, we don't break down the adrenals into different constituents. There are some regions we do. So one example is the lung, where we have multiple constituents, both in terms of source regions and target regions in the lung. Another example is a distributed tissue like the lymph nodes, where we actually have extrathoracic lymph nodes that are modeled separately from thoracic lymph nodes, which are modeled separately from systemic lymph nodes. And then we have a method for combining the dose to all those different constituent parts.
Awesome, and thank you. One more question. I don't know if there's been an intake of plutonium fluoride in the past, but if that were to be modeled, how would you account for the alpha N reaction? It doesn't seem like neutrons are easily modeled with this.
Yeah, so Nolan Hertel's kind of been fascinated by that alpha N contribution to the dose. So he's actually presented some preliminary work on that. Had a student, one of his students did some of that. The alpha N, the appropriate place in our calculation for an alpha N to show up would be in the alpha SAF. And for large tissues, right, organ at the organ level, for example, these are going to be ones and zeros. And the alpha N, frankly, isn't going to have a huge impact, certainly on that self-irradiation. Would the neutron generated by the alpha N contribute some dose to the surrounding tissues? Well, that's one of the things he's looked at. Frankly, I don't expect that to be a significant contributor. It's not going to move one of our dose coefficients that we care about for radiation protection, but it is kind of an interesting dosimetry problem.
Oh, thank you.
Are there any other questions?
Can you hear me?
Yes.
I have a question.
Yes, please.
Okay, good. Yeah. It seems to me going forward, we have two different areas. We have this the dosimetric problem, which is it's basically all known physics and putting it together. It has to, conceptually, it really has to do with you take the body and you represent it numerically as a phantom. And so each, you can imagine each little volume element of the body as a possible source, and then identifying targets. And so it's sources are precisely defined, and it's and then we contrast that with the field of biokinetic modeling. And in biokinetic modeling, there's some theoretical ideas like the pharmacokinetic ideas about, because we have a circulatory system that's pumping things around. And then, and then we have some notion of the chemistry is happening, and we have limited data. Well, let's go back, because when I started in this field, we were talking about plutonium excretion, urinary excretion, which goes way back to Langham, and then there were refinements of that, but that was basically the data, was urinary excretion. And then using compartmental models, you could fit that data. You could fit it. Langham fitted it with a power series, a power function. But anyway, using compartmental models, then the next step was to put names on what these models were. This one is the bone, and this one's the liver, and so on. And then there was some connection with data, but for biokinetic modeling, I think it might, I like to think of it, the compartments are A, B, and C, and we have some notion about the existing, about where these things are in the body. And so what's needed is a association matrix from compartment A to the dosimetric sources. And whereas what's being done now is like the dosimetric sources are identified with biokinetic compartments as okay. That's all I need to say. I said it before, but I think it would be good to introduce this association matrix. Now I have a specific question, and perhaps I could email you about it, but it's about the bone marrow region. It's being divided up in two different ways. One is the yellow marrow and the red marrow, and the other is the trabecular and cortical marrow. And it's describing a as usual, it's describing a physical region of space. And so there are, you could divide up this physical region into non-intersecting portions. You could, instead of having these, you could have 4 non-intersecting regions. And there's certain relationships that have to happen. I found that wasn't the case for the AFs that I was able to extract for plutonium, for alpha. That this really, I can email you about that. That the relationship was not satisfied. It's like, basically if you have a region of space that's divided into two subregions, then the mass of the entire region times the AF tuning target from the entire region is equal to the mass of the subregion times the AF from the subregion to the target, the sum over all the subregions.
I think definitely email me about what you've done there. You're absolutely right. We do have, because of the biokinetic modeling, we do have 2 different treatments for the marrow region, right? And depending on the case, we're either going to have a biokinetic model that uses red and yellow as the 2 constituents of marrow, or there are cases like that plutonium that I just showed you, where the 2 treatments of the marrow region are trabecular marrow and cortical marrow, but yeah, we did spend time making sure that those 2 treatments were consistent with one another. That while it is definitely, we have a preference that folks use the red-yellow treatment because we think that's where the dosimetry was performed, and so we like that. We do think if we have a model like that plutonium where we treat it as trabecular cortical, we are doing the dosimetry in a consistent way. So that's definitely one of the more complex examples where we have to dive in to make sure the SAF is consistent with those 2 different treatments of marrow.
Yeah, the point would, if you describe the phantom, then I could do it. I could take the disintegrations in the so-called trabecular marrow, and I could assign it to the red and yellow. Well, no, I couldn't quite do that. Anyway, this gets into detail, but I'll definitely email you. And thank you for your presentation.
Thank you.
Okay.
Are there any further questions?
Yes. Sorry, one more. This is Brett Rosenberg again. You mentioned that these absorbed fractions better account for behaviors of progeny relative to the parent, notably solubility.
So I think more generally, rather than talking specifically about solubility, if we take that radium case where we have progeny that's radon, when radon is created in that biokinetic calculation, it will now behave with as radon would normally behave in the body. And the prior generation of these calculations would have treated radon as if it behaved chemically the same as its radium parent. They knew that wasn't true, but that was an approximation that was made at the time to be able to perform the calculations. Does that help a little bit?
I'm sorry, still fuzzy. I understand that EMBA does something with the americium ingrowth with plutonium. perhaps you could speak to that difference, if there is much.
Yeah, so I presume, I'm not an IMBA user, but I'm going to presume that IMBA is using one of the newer biokinetic models where progeny is treated as having independent biokinetics from the parent. And so in that case, the modeling of the americium is going to behave as an americium biokinetic model, as opposed to previously in the older generation of biokinetic modeling in the ICRP, they would have had to treat that americium the same way that its parent would move around the body, right? So there's a variety of factors that could be driving why one element moves a certain way. What's nice now is we have biokinetic models that look at the physiology and biochemistry of that particular progeny member and treat it appropriately.
Okay, cool. Thank you.
Are there any further questions?
Hello, it's James here. I haven't got a question, but I just wanted to make a comment on just to confirming IMBA. IMBA assumes shared kinetics, so it assumes that the decay products behave like the parent, and the only exception is for radium-226, where it assumes independent kinetics, because it can make simplifying assumptions. But the new dosimetry program Taurus from PHE that implements the new OIR series, and in that series, independent kinetics are assumed, where the decay products behave like themselves, not like the parent. But I just wanted to confirm that.
Great, thank you.
Okay, and thank you for your presentation.
My pleasure.
Are there any further questions?
Yes, I'm Begoña Perez, and I have two questions. You calculate those assuming homogeneous surface distribution, but does it really happens in that way? And the second question is that there are some software to calculate children dose.
So the first question I'll answer, I'm going to ask you to repeat the second question in a moment, because I didn't quite catch it. But the first question, you're absolutely correct. We are certainly still computing an averaged dose quantity over the target region, and assuming uniformity in terms of the distribution of source material within our source regions. I will point out that within certain regions, like the respiratory tract and like the elementary tract and the skeleton, we now have definitions of our targets and source regions which are pretty small. So they allow us to get at some of the non-uniformity in some of those regions, right? But certainly, we are computing an average quantity over those regions. So, and then could you please repeat your second question?
Yes. Are there any software to calculate children dose? Any software to calculate children doses?
Software to calculate, did you say children dose?
Yes.
Yeah, so I'm not a software developer. James, is Taurus going to have that ability? I presume it doesn't have it yet to do doses to the children.
Okay, that's right. At the moment, it's Taurus is for workers. So, but kind of in the future, we plan to have software that we'll also do for members of the public.
In the United States, Keith Eckerman's the author of Decal. He's working on a revision to that that will be able to do dose coefficients in the children using these same methods. So.
Okay, thank you.
Any further questions? Well, I appreciate everyone's participation and particularly the excellent presentations our two guest speakers have given today. So I'll have to talk to Liz later because she had to run, but Derek, thank you very much. And as I mentioned, we'd like to continue these presentations as long as there's interest. If you have any requests for people you'd like to hear from, please do contact me by email and we'll see what we can do. The next meeting will probably be in mid-January. All things being equal, if we're still here and we can still have presentations, we'll make it happen. Thank you very much, and we look forward to the next presentation set. Bye-bye.